In this video, I will talk about a problem in quantum mechanics that will help you to visualize and or understand the beauty of the perturbation theory, that which I had discussed before in one of my earlier videos. So let's talk about the problem, right? Okay, so the problem is that we have a sphere and on which we have an electron bounded to that sphere in such a way that the electron shall move only on the surface of the sphere, right? So let's draw that over here. Let's say that this thing over here is a sphere. Even though it looks like a circle, imagine it's in 3 dimension, so it's a sphere. And say that there is an electron over here, right? And the electron from center is at some position r, right? So say that's the radius, that is r. Okay, now the problem is that this whole thing over here is in a magnetic field, and that magnetic field is some b, that is b1, and say that it's in my, let's say, y direction, right? So it's in my y direction. Okay, so therefore this electron on a sphere is in some perturbation now, right? Okay, so first let's go ahead and recall some of the things. So from classical mechanics, first let's recall that from the classical mechanics, for a particle on a surface of a sphere, right, the Hamiltonian H is given as L square over 2I, right? Okay, so to upgrade from classical to quantum, we have to upgrade these quantities. Here what I'm going in quantum mechanics. Let's upgrade these quantities to operators, right? So H hat, that means that it's the H Hamiltonian operator, L square operator over 2I, right? I'll write I once again, I, right? Okay, so with that the case, we also know that the zeroth order states are the angular momenta states, right? So the L M states. Okay, so these states that are equal to some y m l theta and phi, right? This YML theta phi are the spherical harmonics, and they occur whenever one solves a partial differential equation that involves a spherical symmetry, right? Okay, so now also note that this particle or this electron over here is confined to the surface of a sphere, implying that my r, all of this time when it moves around on the surface of the sphere, the r is not going to change, right? So the derivative with respect to r just vanishes, and so because my psi, the wave function, is independent of r, right? Okay, so well, just to add this thing, that if you don't understand anything, you could just go back and start the video again, or from wherever you did not understood what I was talking about, right? Okay, let's come back and let's see one of these other things, right? That the energy, or first let's just compute the energy, right? The energy eigenvalue for this problem. So my Hamiltonian is actually the total energy of the system, right? So I'm going to use again one of the things that I've been using in almost all of my videos, that when my Hamiltonian acts on some state psi, it returns with E constant energy eigenvalue and state psi, right? So this eigenvalue equation is actually very important. So now using this, let's see what my E would be, right? Also recall or note that whenever my L square operator acts on some psi, it throws out or spits out the eigenvalue h bar square L into L plus 1, where these L's, these small L's, they are just my angular momentum quantum number, right? Okay, so, and also not to forget, it returns my state psi back, right? So the eigenvalue of my L square operator is then this thing over here. And now let's use this equation and let's put the Hamiltonian, this Hamiltonian, in this eigenvalue equation, right? So let's do it. So I'll have my L square operator over 2I acting on psi is equal to E psi, right? Well, we have just seen from this thing over here that when my L square acts on psi, I get this thing over here, right? So then I'll have over here my h bar square L into L plus 1 over 2I psi is equal to E psi, right? And so while I'm doing this mathematics, you should be understanding the physics that's happening. So this tells me that my E is then equal to this thing over here, or actually let me write it down. I'll write it down over here, okay? So my E is then equal to h bar square L into L plus 1 over 2I, right? So here now I have my energy eigenvalues, right? So then let's move on to next page, right? Now this, before I go on to the next page, let me mention that this energy eigenvalue is my zeroth order energy, right? Because this energy eigenvalue is just for when a particle or an electron is confined to my surface of the sphere, right? But without any perturbation term, without any this thing over here, or magnetic field or whatever, right? So this is my zeroth order energy, right? Zeroth order E. Alright, let's go ahead on the next page. Okay, so the next thing is to note that for all of my L, right, I'll write it down over here. That is, for all L, there exists, this symbol over here is a mathematical symbol for there exists, 2L plus 1 values of M, right? 2L plus 1 of M states, right? And this is because the energy is independent of the magnetic quantum number, that is this M over here. And so then each energy level is degenerate, right? And so if each energy level is degenerate, then I'll have to use degenerate perturbation theory, right? But eventually we will see that this degenerate perturbation theory for this problem will reduce back to non-degenerate perturbation theory, and which I have already made a video on, right? Okay, so let's move on, and also note that the Hamiltonian of such a problem can be then written as negative mu dot b, right, where mu is my moment, my magnetic moment, right? And so also then recall that this magnetic moment is equal to negative E over 2m, where m is the mass of the electron times my angular momentum L, right? So, but we are doing quantum mechanics, so I'm going to upgrade that to the operator form, right? So this putting a hat on top of L is just writing it as an operator, and whenever we want to upgrade from classical to quantum mechanics, or say quantize our quantity, right? So we just write this as an operator, right? L hat. Also know that my angular momentum is quantized, right? So let's move on and put this value of mu, magnetic moment, in my H on this right hand side, right? So when I do that, then this thing over here is then equal to negative E over 2m L hat dot B, right? So now B, or I'll just write it as B prime, as it's my perturbation, right? Or B prime over here. Okay, so but then the problem was, as you can see here, that my B, this B prime, I'll call it B prime, is then B1 in Y direction, right? So, well, then let's substitute for B and write this thing as, first let me write over here that my B prime is my B1 Y hat, right? So also then know that my L can be, because it's a vector, right? So it can be written as in components, that my Lx x hat plus my some Ly y hat in y direction plus Lz in some z direction, right? So this is the components of my angular momenta. Okay, so now note that if I do this L dot B, right, the only component that survives is, because B only has Y component, so the Y component only shall survive when I do B dot L or L dot B, right? So because you can see that Y dot X hat will be 0, Y dot Z hat will be 0, but Y dot Y hat will remain or will survive. So then I can write my H prime as equal to, where this H over here was also prime, right? It's the perturbation or the perturbed Hamiltonian, right? Negative E over 2m, where again m is the mass of the electron, Ly times B1, right? So y hat dot y hat equals 1, and therefore this is the Hamiltonian that I'm left with. We are going to simplify this a bit more, because we know that there is another quantity called the Larmor frequency, and so we can just use that and simplify this long looking Hamiltonian, right? So we can shorten it more, and so if we can, let's just do it, right? So I'll do that on the next page now. So now let's write our Larmor frequency as omega 1 being equal to E B1 over 2m, right? So this frequency over here is called the Larmor frequency. Alright, so for those who do not know what Larmor frequency is, well, very shortly, it is just the frequency of the precession which is related to the strength of the magnetic field applied, right? Okay, so well, with then this over here, let's go back, this my Hamiltonian over here, right? This Hamiltonian can then be simplified and written in terms of Larmor frequency omega 1. So you can see that my Larmor frequency, let's go back here, is EB1 over 2m, right? So let's go back and see, we have EB1 over 2m, so my H prime can then be written as simply H prime is equal to negative omega 1 Ly. Okay. Right. So, well, now the only L component of my angular momentum is in my Hamiltonian, and therefore the Ly, or the yth component of my angular momentum, is going to be the eigenbasis for my perturbed problem, right? And well, the best part about that is that in my Ly eigenbasis, the perturbation is then diagonal, right, in my degenerate subspace. So if that is the case, then it implies that my degenerate perturbation theory, dPt, reduces to non-degenerate perturbation theory, right? So, well, you can see that we chose a problem that my B was in y direction, so we can reduce or degenerate to non-degenerate perturbation theory. Right, so now let's just recall that from our non-degenerate perturbation theory, time-independent non-degenerate perturbation theory, that the energy corrections, right, are written as H n is equal to psi n zeroth order, right? H1 psi n zeroth order. So this is then again just the expectation value of my perturbed Hamiltonian, and this, from this I can compute my, you call, the first order correction to the problem, right? First order correction to my energy, so which is then written as, or let me just write it on the next page, right? Okay, let's go here and let's write it down over here. So now it's just some algebra that I'm going to be doing. If you remember that how we derived this, so my first order correction to my En is then going to be bra psi n zeroth order, right? My perturbed Hamiltonian H prime, or H1 as we called it, psi n 0. So it is the diagonal matrix element of my perturbed Hamiltonian, right? Now also note that, or rather recall, as I mentioned before, that my zeroth order states for this problem are my angular momenta states, which are then L, M, but My, right? And we have my perturbed Hamiltonian as omega 1 Ly. So with these things over here and this expression over here, let's just substitute the values. So E1n is then written as Lmy omega 1 Ly and again Lmy, right? So the expectation value of my perturbed Hamiltonian in my angular momenta states. Well, now also note that when my Ly acts on My, so Ly acts on My, so they're in the same basis, I'll have My times H cut and my state back, that is My, right? So again, this is just the eigenvalue equation for Ly. So with this thing over here and this thing over here, or let me just shorten it out, sorry, this thing over here, I can simply compute my En to first order, which will then be E1n is equal to Lmy, but my Ly acting on my Lmy gives me My H cut, and I also have this omega over here, omega 1, so I'll have omega 1 My H cut and my state Lmy, right? Okay, so remember this thing over here now, and let's move on to the next page. Now everything is simple, we have almost solved our problem. All we have to do now is, I'm gonna write the previous thing down here again, Lmy omega 1 Ly Lmy. Alright, but now omega 1 and Ly, actually I have written this equation over here. When I solved this, what I got was Lmy and omega 1 times my M1 or My H cut Lmy, right? Let's go back and check. Lmy omega 1 My H cut Lmy, right? So that's it, right? Now let's see that My omega 1 and H cut over here are just some constants, and therefore I can pull them out of this inner product. So omega 1 My H cut become outside, and I'm left with Lmy Lmy. Now again, note that my states, or these angular momenta states, they are normalized, and because we start off with normalized states, and so if they are normalized, then this inner product goes to 1, and so this thing is equal to then simply My H cut or H bar times my omega 1. Right, so this is then therefore my energy corrected up to first order En is equal to, or it's equal to My h cut omega 1, right? Yeah, so actually instead of calling this as En, I should instead call it Em, right? Because it's dependent on the magnetic quantum number, not the principal quantum number. And well, let's see that my E0, the zeroth order energy, that was El actually, is equal to, that was equal to my h cut square over 2I L into L plus 1, right? We derived this, and therefore my total corrected energy up to first order will then be equal to the correction that was up to zeroth order, or the zeroth order correction, or the unperturbed energy, that was L into L plus 1 plus M y h cut omega 1, right? So this will now be the total energy up to first order of my perturbed system, that was my electron moving around the surface of a sphere in a perturbed field, the magnetic field that was along my y direction. So this was just one of the too many problems actually that we can solve using the perturbation theory. And the perturbation theory simplifies a very complicated problem. There could be more problems that are like that involve the harmonic oscillator, or particle in a 2D plane or a 3D box or cube, that is to say, in some perturbations or some potentials that could be periodic or non-periodic, or exponential potentials, right? And so we can use this perturbation theory and solve those kind of systems and get their physical quantities, such as the energies, their angular momenta, and so on, or even their states, right? As you remember that I also derived an expression to find the first order states of my system if it's perturbed, right? So it is actually, the perturbation theory is extremely useful to quantum mechanics. It is one of the approximation methods. As you can see, that this energy that I computed over here is approximate solution, or the approximate energy of such a system that I described in this problem, right?